In 7.9, we are going to do just a basic introduction to differential equations. There is a completely different course later on called differential equations. We can spend several semesters learning these types of equations and how to solve them and all the different applications that go along with them. But here in Calculus 2, we just want you to become familiar with the idea of what exactly a differential equation is, and just how to solve a basic one. So to start with, a differential equation is just an equation that contains a derivative. So there's lots of different forms that we have learned for derivative, and you might see any one of them. So I'll show you a few examples of what these might look like. So these are all differential equations. Now we're not going to solve these right now, but just to give you an idea, really the only criteria is it's an equation that contains a derivative. So dy dx, that's one of the formats we learned for writing derivative, plus 5y minus 2 equals 3x. So we've got an equation that contains a derivative. So it's a differential equation. We could also have y double prime plus 4y prime minus 5y equals 3 cosine x. It is an equation that contains a derivative. It actually contains two terms that have derivatives. The prime notation is just an alternative notation for saying derivative. So y prime means first derivative. Y double prime there in our first term means second derivative. So it doesn't always have to be just first derivative. We could go to higher order derivatives as well, and those would also count. Two y cubed dy dx minus 3x squared y equals 5x. There's no rules about the x's and the y's. When just deciding if we have a differential equation, all we're looking for is that we have an equation that contains a derivative. And that makes it a differential equation. So all these are just different examples of some types of differential equations. There's only one specific type that we're going to be solving here in 7.9 because it doesn't involve really any new math. It just involves learning this new idea, this new concept of a differential equation, and just using math that we already know to solve them. So now that we know what a differential equation looks like, the solution to a differential equation is a function. It is the original y function that is in that equation that we're given. It's the original function. I'm going to call it y because I used y as my dependent variable in all these examples, but it's the function y that would satisfy this equation. So if we were to try to plug it back in, the left-hand side and the right-hand side would equal out. But the most important thing to understand is that the solution is a function. It's not like algebra when we solved equations in algebra and our solution was always x equals a number. So in differential equations, the solution is going to be a function. We very often call it y of x because y is the dependent or output variable and x is the independent or input variable. So when we're asked to solve a differential equation, our goal is always going to be to find a function, figure out a function that's going to make that equation work. So before we can talk about how to solve a differential equation, because there are lots of different ways to solve a differential equation, you first have to classify the differential equation, because very often how you solve it is going to depend on several different things that we see in the differential equation. And the first one is the order of the differential equation. So the order of a differential equation is just the highest order derivative that you see throughout the equation. We solve first order equations very differently than we solve second or third or fourth order equations. So even though we're only going to be learning how to solve one type here in 7.9, if down the road you were to actually take a course in differential equations and you were to learn lots of different solving methods, most of those methods are going to be dependent upon the order of the differential equation. So it is the highest order derivative that appears in the differential equation. And this is the last time I'm going to write differential equation. You're usually going to see differential equation abbreviated as DE. And that's not just my laziness. That's actually a pretty common within mathematics for differential equations to be DEs. So let's look at a couple of examples. We're going to, for now, just identify the order of each differential equation. So we've got dy dx plus 2y equals 5x cubed. All we want to know right now is the order. And the order is purely dependent upon the derivatives that we see in there. And we only see one derivative in this problem, and it is a first order derivative. Dy dx means the derivative was just taken once. So this is first order. Or you could say order equals 1. Some of the problems my differential equations class is actually solving right now are 2y double prime minus 5y prime plus 6y equals 3e to the 5x. It's an equation that contains derivatives, so it's a differential equation. All we want to know is what is the order. So the order only has to do with the derivatives that we see. So y prime represents a derivative. Y double prime also represents a derivative. But we can't say both of those. I can't say first and second. Order only refers to the highest order derivative. So 2 is bigger than 1. So this guy wins out. And this is second order. Or we could say that the order equals 2, because that equation contains a second derivative. And one more really quick, 2y and then d4y dx4 plus 3x d2y dx2 equals 0. We've got another differential equation here. We just want to know the order. So both of these dy dx's represent derivatives, and those superscripts we see, the 2 and the 4 are not powers. They're not exponents. They represent how many times the derivative was taken. So on this term here, they're saying you're going to take the derivative of your y equation twice. And then on this one here, they're saying take the derivative of your y equation 4 times. And remember, the order only refers to the highest order derivative. So this one is going to be fourth order. Or we could say that the order equals 4. So when you're talking about the order of a differential equation, all you're looking at are the derivatives that you see in the equation, and we just want to know the highest order derivative. The second way that we need to classify differential equations is if they are linear or nonlinear. And this is sometimes confusing to people because it's very different than how we define linear equations in algebra class. It's not like that at all. So this is completely different. It's got the same general meaning as linear. So linear means first power. So that's still true. So linear means it's got to be a polynomial, which means we don't see any square roots, we don't see any trig functions, we don't see any negative powers. Polynomials are just addition between the terms, and then we can have real number coefficients, and then all of our variables have positive whole number powers. So linear means a polynomial where the largest power is a 1. So that part is still true. But one thing that's going to be very different here with differential equations, in algebra, we decide something is linear based on the independent variable, which is usually x. For differential equations, we decide if it's linear or nonlinear based on the independent variable. So this classification is based on all forms of the independent variable. Excuse me, I just said independent. The classification is based on all forms of the dependent variable. Dependent. And typically, the dependent variable is the y variable. So we want to make sure all instances of the y, and that includes the derivative for y. So y and its derivatives. Every time we see a y or some form of derivative of y, we need to make sure it's linear in order to call our differential equation linear. Now, if we see any y's that are not linear, any derivatives that are not linear, or if we see y's being multiplied by a derivative, that's technically two forms of y being multiplied together. So if you think about in algebra class, what happens if you multiply two y's together? You get y squared. So it's the same thing here, even though we can't actually multiply y times the derivative of y, it technically raises that equation to a different order, polynomial-wise, because I'm multiplying forms of my y, and that would not be linear. So we're still looking for, we're still using linear in the polynomial sense of the definition of the word, where largest power is 1, but classifying a differential equation as linear or nonlinear is based on the dependent variable, all forms of the dependent variable. That means y and all of its derivatives. So let me show you some examples of some linear and nonlinear equations, and we'll talk about why exactly they are linear or nonlinear. So you've got 2y prime minus 5xy equals 3x squared. So when you're deciding linear and nonlinear, what you should do is you should go through and find all forms of y and its derivatives. So there's a y prime and there's a y. First, check to make sure that they don't have any powers on them. They're not inside of any nonlinear functions like trigonometry, exponential, logarithms, anything like that. So in this case, neither one of them are. I've got just y prime times a 2, and I've got y times a 5x. So the y's themselves are linear. There's no exponent written here, so we can assume it's a 1, which means linear. The next thing you should make sure of is that you don't have any y's being multiplied together, because that would be nonlinear as well. Any y's or any other forms of the y, like its derivative. And I don't. The only thing being combined with my y prime is a times 2, which is perfectly fine. Coefficients are fine. And the only thing being multiplied by my y here is a 5x, which is the independent variable. And that is also perfectly fine. Linear or nonlinear is based solely on our dependent variable, y and its derivatives. So you're going to look at your y prime and your y, or your y double prime if it's a second order equation, or so on, and make sure that every single time you see a y in that problem, that it's contained within a linear term. So power of 1, and it's not multiplied by any other y's. It's not inside of any nonlinear functions. So this is an example of a linear differential equation. I don't have y's inside of any trig, inside square roots, inside of exponentials, and I don't have y's multiplied together. So this one is linear. Our next example, 2y dy dx plus 3x to the 5th equals 2 cosine x. Now we do not care about the x's at all. The x is the independent variable. And to decide linear, all we care about is the dependent variable. So go through and find all forms of your dependent variable. So I've got a y, I've got derivative of y, and those are my only y's in the problem. Now, individually, they're both raised to the first power, so that's good. No power means first power. The problem with this one, though, is these guys are multiplied together, and that's bad. Think back in just basic algebra. If this was y times y, it would technically be a y squared, which is not linear. Now, even though we don't have y times y, we have y times dy dx. Dy dx is a form of our dependent variable. So any multiplication between different forms of our dependent variable would deem it non-linear, like we have in this case. So because I've got y times dy dx, this one is non-linear. I'm going to do two more examples. Y double prime minus 5y prime minus 6y equals 3y sine x. So if you look through and find all of your y's, make sure all of them individually are linear and that none of them are being multiplied together. So individually they are all linear. None of them have a power written. None of them are inside of any nonlinear functions. So they're all power 1. And then none of them are being multiplied together. The 3 on the left are being combined with subtraction, and coefficients are perfectly fine. They don't affect linearity. And then there's a y on the right. It is being multiplied by 3 and sine x, but that's perfectly fine because 3 is just a coefficient, and sine x includes our independent variable. So that's not an issue either. So everywhere I see a y or some form of y, we've got to make sure that it's linear and that none of them are being multiplied or divided, technically. Although we probably will not see division. But hopefully you remember from algebra that multiplication and division are really the same thing. Multiplying is just dividing by the reciprocal. We can always switch back and forth between multiplication and division whenever we need to. So this one's linear. All right, the last one. d4y dx4 minus 2 root y equals 3x. What do you think? Is it linear or nonlinear? Find all instances of y. So that first term represents the fourth derivative of y. And then I have a square root y in my second term. The 4's on that derivative, remember, those are not exponents. That just means we've taken the fourth derivative. No problem there. That has to do with the order. So my first term is just y to the first power. It's not being multiplied by anything else that has y's in it. So that first term's perfectly fine. Now the second term is not being multiplied by any other y's, but square root of y is not linear. Technically, square root of y, we can think of that as y to the 1/2 power. And linear means first power, means the exponent is 1, and a square root is a 1/2 power. So that's where this guy goes wrong. Because we have y inside of a square root, which is nonlinear, this entire differential equation is going to be nonlinear. Okay, so we've learned two ways to classify differential equations, and In other classes, as we learn multiple solving methods, classifying is going to be really, really important. Before we actually talk about solving differential equations, the last thing, kind of preliminary, that I want to talk about is verifying solutions. How do we verify that something is a solution to a differential equation? Well, remember, up here at the top, we said the solution to a differential equation, the solution of a differential equation is a function, y of x, that satisfies the differential equation, which means if I were to take my y of x and plug it in to the original differential equation, it should make the equation true. We use a very similar definition in algebra when we're solving for x. We know something is a solution to an algebraic equation, like x equals 5 is a solution, if I can plug 5 back in for x and the equation is true. So it's a very similar concept. The only difference here is we don't only have y in the differential equation. We also have possibly y prime, y double prime, fourth derivative of y. So we're not only going to plug y into the spot where we have the y, we also need to figure out the derivatives and plug them in as well. So we need to replace y and its derivatives. In the differential equation. And check to see if it makes the equation true. Now, the only time an equation is true is if you get the exact same expression or exact same value on the right-hand side and the left-hand side. So there's a little bit of planning and a little bit of kind of pre-work that goes into verifying these solutions. We've got to scan through our differential equation and look to see what kind of derivatives are in there as well. And we have to calculate those derivatives ahead of time so that we can go ahead and replace all of that stuff. We're not just replacing the y. We will also be replacing dy dx or y double prime with the derivatives of the y that we're given. So is y equals 3e to the negative x a solution of the differential equation y double prime plus 2y prime plus y equals 0. So this is our potential solution. This might be the answer to this differential equation. Remember, the answer or the solution for a differential equation is a function. It's a function that makes the equation true. So if you look at your differential equation, I have a spot to put that y function, but I also need y prime and y double prime in order to thoroughly check this. So before I start replacing, I need to figure out what those are. So we're given that y equals 3e to the negative x. We also need to know y prime and y double prime. All of those need to be replaced. So if y is 3e to the negative x, y prime, remember when you do derivatives, the coefficient just transfers. The derivative for e to the negative x, the derivative of a e is always itself, but then you also have to multiply by the derivative of the exponent. So y prime is going to be negative 3 to the e to the negative x. And if we do that again, we're going to have another negative come out, and it's going to change it back to positive 3 e to the negative x. And we want to plug all of this stuff back in. So the y double is going to go there. First derivative is going to go there. And then original y is going to go here. We're going to plug all those in and see if we get 0 when we do that. So y double prime is 3e to the negative x, and then it says plus 2 y primes, and y prime is negative 3e to the negative x, plus y, which is 3e to the negative x. We want to know if this is going to equal 0. Now, once we get all that stuff plugged in, we've just got a little bit of algebra to do. So in that middle term, I've got some multiplying to do. 2 times negative 3 is going to be a minus 6. Oops. And these are all like terms. They all have an e to the negative x in them. So we can combine them by combining their coefficients. So I've got 3 minus 6 plus 3. So 3 minus 6 is negative 3, plus 3 more is 0. I've got 0 e to the negative x's. And anything times 0 is 0. So it's true. 3e to the negative x is a solution for this differential equation. We found the derivatives that we needed, we plugged it all in, and then we worked out the algebra, and we got a true equation. We got the same exact value. Sometimes it'll be an expression, but we got the same thing on both sides of the equation. Now don't move any terms from the left or right. We're not trying to solve anything here, we're just trying to simplify. So just simplify down your left side as much as possible. If you need to, simplify your right side down as much as possible, and then just see if they match. That's all we're trying to do. So our answer here is yes. When we used that y equation and plugged it back in, we got a true statement from our differential equation, which means it is going to be a solution. Is y equals 5 sine of 3t a solution of the differential equation y double prime minus 9y equals 10 sine t. Sine 3t, sorry. Is y equals 5 sine of 3t a solution of the differential equation y double prime minus 9y equals 10 sine 3t? So this time t is our independent variable, which is perfectly fine. We're not going to treat this any differently. Y is the dependent variable. Before you start plugging things in, scan your differential equation and look to see what you need to do this problem. We need the original y, which was given, so that's good. We also need y double prime. We need second derivative. So we can't plug in until we've got we're not ready to plug in until we have our second derivative. We don't need our first derivative though, but if you remember from Calc 1, you really can't get your second derivative without getting your first derivative. So we will go through our first derivative to get there. So if y is equal to 5 sine of 3t, We're going to have to do the chain rule again here. So the derivative for sine is cosine, same angle, but then we also have to multiply by the derivative of the angle, which is a 3. And we already have a 5 in the front, so 5 times 3 is 15. Now we don't need y prime to answer this question, but we do need it in order to get to y double prime. And we'll do that one more time. The derivative for cosine is negative sine of the same angle, and we have to multiply by the derivative of the angle. We already have a 15 in the front. We've got to multiply by another 3, so it's going to turn it into 45. Negative 45 sine of 3t. So we're going to take the y equals 5 sine 3t and plug it in here. And we're going to take the y double prime equals negative 45 sine 3t and plug it in right here and see what we get. We're going to see if it makes this equation true or not. So our equation says y double prime, and I'm going to replace that. That's negative 45 sine of 3t minus 9 of your y's, which is 5 sine of 3t. Is that equal to 10 sine 3t is what we're trying to figure out. So from here it's just some algebra. We've got some multiplication we can do here. So negative 9 times 5, that's going to be negative 45. And these are like terms. They both have sine 3t in them. So we can combine their coefficients and consolidate it down to a single term. I've got negative 45 of them, and I'm minusing 45 more. That's going to give me a total of negative 90 sine 3t. Is that equal to 10 sine 3t? Now there might be certain values of t where it will work, but that's not what we're interested in. We're interested in getting the exact same answer, or the exact same expression, or the exact same value on both sides of our differential equation. And we don't. The coefficients are off. I've got negative 90 on the left, I've got 10 on the right. So this is not true. This is not always going to be a true statement. There's probably only select values of t that this could work for. We're looking for a function y that is always going to work. And this one does not. Because when we work it out algebraically, I've got negative 90 sine 3t equals 10 sine 3t. Again, don't try to move one of those over to the other side and combine them and solve. We're not being asked to solve for t or anything like that. We're just being asked to verify if something is a solution. So we replace all forms of y and see if it makes the equation true. And in this case, it does not. My left-hand side does not match perfectly with my right-hand side, so it's a no. So y equals 5 sine 3t is not a solution for y double prime minus 9y equals 10 sine 3t. So what is a solution? So finally, we're going to talk about actually solving a differential equation. But this is just our basics for now. So we have to know how to classify them, because as we learn more solving methods, the solving methods are going to be based on the order of the differential equation and whether they are linear or nonlinear. And then it's also very important to be able to check your answer, to check your solution. Does what I found really work?